By 1900, it was clear that the model of the atom that Dalton had put forward no longer worked. The discovery of the electron in Cambridge by Thomson, the work of the Curies in Paris, and the discoveries made by Rutherford in Montreal showed to many physicists and chemists that the atom could be broken up. While some denied the evidence pointed to a new understanding of matter, the physicists associated with the Cavendish Laboratory turned once again to the long-standing British tradition of trying to create models of physical systems to gain insight into the constituent pieces of the universe. What this led to was a revolution in our understanding of the nature of matter. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 12, The Divided Atom, Part 3, New Models. The discovery of the electron by Thomson clearly indicated that the Daltonian model of the atom was insufficient. If cathode rays were, in fact, pieces of charged matter, then they had to be coming from somewhere. And since all matter was made of atoms, this meant they had to originate from those atoms. So the question was, how are electrons arranged in the atom? The earliest attempt to answer that question came from the man who had directly observed that the cathode ray was negatively charged. In 1901, French physicist Jean Perrin suggested that each atom consisted of one or more positively charged bodies being orbited by small, negatively charged electrons in direct analogy to the much smaller planets orbiting a larger and more massive sun. He also said that the total amount of negative charges in the electrons would be exactly equal to the positive central charge or charges. In his words, written for Revue Scientifique, quote, "Each atom will consist of one or more highly charged positive bodies, a kind of positive sun, whose charge is much higher than that of a corpuscle, and also of a kind of small negative planets, all of these bodies gravitating under the action of electrical forces, and with the total negative charge exactly equal to the total positive charge, so that the atom is electrically neutral." Just as importantly, to foreshadow a topic we'll discuss in our upcoming episode on the quantum atom, Perrin wrote that, quote, "The gravitational periods of the different masses in the atom might correspond to the different wavelengths of light revealed in the rays of the emission spectrum," unquote. What's interesting here, I think, is that Perrin is struggling with his analogy. What we now know is that gravitation has fairly little to do with what's going on in the atom. The dominant interaction responsible for the presence of bound electrons is that of electromagnetism, which, while similar to gravitation in how it is represented mathematically, is much stronger. We also know that it is electromagnetic oscillations that are responsible for light. However, given that Perrin's model is so rooted in a planetary explanation, he is almost irresistibly drawn into discussing it in directly gravitational terms. Finally, it should be noted that Perrin makes no attempt to develop his model beyond the descriptive stage. While very intriguing, his discussions are merely speculative and are meant only to provide a direction for further investigation and research. His paper is what we call a, quote, review article, wherein a scientist who is prominent in an area of research summarizes what has gone on in the field for broader scientific communities to access. The next model we want to talk about is a similar one in some respects, but to understand its origin, we need to step back in time about 45 years. In 1859, physicist James Clerk Maxwell had developed a very strong mathematical description of the rings of Saturn that had shown how such a system was stable over the long term if it were made of discrete objects. As you may recall from an episode in the first series of this podcast, scientists often use mathematics as a tool for modeling physical systems. In this process, the scientist will use mathematical expressions of various natural laws, in this case gravitational attraction and orbital motion, to work out the consequences using deductive reasoning. If those results accurately describe the behavior of the real physical system being considered, then there are two things that are believed to be true. First, the mathematical description is thought to be a good model of the system, and the success of the model is said to provide evidence of the accuracy of the original description of the foundational physical laws. Maxwell's mathematical model of Saturn's rings was considered by many of his time to be the definitive demonstration of the accuracy of Newton's laws of motion and his universal law of gravitation. It was also a mathematical tour de force for physics in being able to model such a very complex system. As such, it served as a guiding light for attempts to understand other complex systems in the years that followed. One admirer of this approach was a Japanese physicist by the name of Hantaro Nagaoka. Nagaoka had been born in Nagasaki, Japan, and was educated at Tokyo University. During his time in the school, a number of British scientists traveled to Japan to work on problems related to seismology, and after graduating in 1887, Nagaoka worked with one of them, Cargill Gilston Knott, on topics related to magnetism. In 1893, Nagaoka traveled to Europe, where he continued his education at the universities of Berlin, Munich, and Vienna. In 1900, he attended the First International Congress of Physicists in Paris, where he heard Marie Curie lecture on radioactivity. This lecture captured Nagaoka's interest, leading him to begin investigations in that area. He returned to Japan in 1901 to take up the position of professor of physics at Tokyo University, where he would serve until 1925. After his return to Japan, Nagaoka took up the problem of atomic structure. As he left Europe prior to Perrin's publication of a planetary model, Nagaoka's work is generally thought to be independent of it. Instead, Nagaoka was guided by the approach taken by Maxwell in understanding the rings of Saturn. Now, at this point, the dates that I've looked up become a little bit sketchy. Some sources I found say that Nagaoka's model dates to 1904 with an article published in the Royal Society's journal, Philosophical Transaction, just after Thomson will publish his model of the atom. However, other sources note that Nagaoka describes the model in a lecture given in 1903, which would just predate Thomson's model. If this is the case, which I'm inclined to accept, then Nagaoka is the first person to develop a mathematical model of the atom with electron structure. Nagaoka's model, which he called the Saturnian Model for reasons that will become apparent, attempted to create a mathematical description of the atom in analogy with Maxwell's approach. He said that the atom consisted of a large, single, massive positive charge, surrounded by small electrons arranged in one or more rings, just like you see the rings around Saturn. His description attempted to show that such a configuration would be stable, and like Perrin, he suggested that this electron structure might be responsible for the specific, unique spectral signatures of each of the elements. Both Ernest Rutherford and Henri Poincaré would cite this model in their later work on atomic structure. The next attempt to construct a model of the atom was made by the man they called the Master. From his perch atop the Cavendish Laboratory, J.J. Thomson put forward an idea in 1904 that has been misstated to students of science for many, many years by well-meaning teachers trying to simplify the model to make it more understandable. Like Perrin and Nagaoka, Thomson knew that matter was neutral. He also knew he had to create something that was stable, at least for most of the elements. However, he was loath to deviate too far from the model Dalton had put forward. Now, Thomson thought that the models put forth by Perrin and Nagaoka had a problem. He felt like they should be unstable. The reason for this was that Maxwell had demonstrated in his work on deriving the expressions that described electromagnetism that charged particles traveling in circles would give off energy. If the electrons did indeed do this, they should spiral or would spiral into the central positive charge of either Perrin's or Nagaoka's model, and thus all of the atoms and the elements they made up would be unstable, not just a few that had been discovered up to that point. Now, the genesis for this new model of Thomson's came from a set of experiments by the American physicist Alfred Meyer, and things that he had done with magnets. Meyer had placed a number of small magnets on cork bobs that floated in water. When a larger electromagnetic coil was placed above this arrangement, the smaller floating magnets tended to form themselves into ring-like structures. Meyer experimented with different numbers of smaller magnets and found that a single ring could accommodate up to 5 magnets. When a 6th magnet was added, a new ring would be formed. Each of these rings was stable, and more rings would be formed as more magnets were added in multiples of 5. In this experiment, Thomson saw a possible structure for electrons in the atom. His model was that the atom had a diffuse positive charge spread out over a certain spatial extent that would create an electric field similar to the magnetic field of Meyer's large electromagnets. Results at this time from work in kinetic theory suggested that the atom was on the order of about a billionth of a meter in size, and so that's how big Thomson thought the diffuse positive charge would be. Inside of this diffuse charge, the electrons would be arranged in ring-like structures in which they could move just like the small magnets in Meyer's experiment. Today, Thomson's model is rather misleadingly known as the Plum Pudding Model after the British dessert, where you have raisins that are sort of embedded in a gelatinous pudding. The problem with this analogy is twofold. First, the raisins in the pudding have no real structure like the electrons in Thomson's models would have had. Second, the raisins in the dessert don't move. They are what we physicists would call static. Thomson's model, on the other hand, had the electrons in what we would call a state of dynamic or moving equilibrium. This model would account for the vast number of electrons that could be removed from the cathode of a Cook's tube, and, more importantly, it might be able to explain something no one had been able to figure out up to this point. If you will recall from a few episodes back, we talked about the idea of chemical periodicity. This was the recognition that the properties of a chemical element seem to repeat themselves in an organized fashion. For example, lithium, sodium, and potassium all have the same physical properties even as they become denser. What's more, they all like to react with chlorine, and bromine in the same way and in the same proportions. Of course, fluorine, chlorine, and bromine all share the same physical properties and chemical properties as each other, just like the lithium, sodium, and potassium do. As we've discussed, over the course of about a decade between 1862 and 1871, several chemists had come up with or created periodic representations of this, culminating in Mendeleev's famous table. We had talked about this being an example of an organizing principle that suggested that there was some underlying physical cause to the regular physical properties and chemical behavior of the elements. The problem was, by the time of Thomson, no one had been able to figure out what that underlying physical cause was. Arrhenius's ideas on ion theory held some hope for the direction of research, and Thomson thought that his electron structure might be the way to explain how periodicity arose. While not quite as mathematically rigorous as Nagaoka's model, Thomson's model explained things that the Saturnian model didn't. The academic discussion of this will play out over the next 5 or so years, and will result in a number of interesting observations. When confronted with this sort of dichotomy of models, I like to take a moment to discuss the pros and cons of each of those models. Before I do that, however, I think it'd be good to take a moment to evaluate what's going on here. The first thing is to recognize the exclusive use of modeling in these discussions. This is a really strong move away from that European approach of a dynamical explanation of physical processes that doesn't posit the existence of specific things, but only talks about forces. Second, this is also something being done almost exclusively by physicists at this point. While Rutherford and Curie have extensive chemical training, there is a notable lack of chemists in the process and the discussion. While I will leave the finer points of why to the historians of chemistry, I think it has to do with the field's grounding in the discussion of reactions and what can be determined from those. For a chemist, the discussions of subatomic particles and all the rest looks a lot like mere philosophical speculation without a lot of physical or chemical evidence to support it, and thus it wasn't likely something that a chemist would think was worth spending a whole lot of time on. Okay, so now let's do our brief evaluation of the two models. Nagaoka's model had a good sense of analogy with a well-understood physical system. It had grown out of an attempt to use the model to explain a well-documented but not understood phenomenon, namely atomic spectra. It posited an explanation for one type of nuclear decay in suggesting that Becquerel's radioactive beta decay, so named by Rutherford, was due to the ejection of ring electrons caused by instabilities that might have developed for any number of reasons. The drawbacks were that the model didn't account for the electron energy decay, and, as Thomson would show, it was profoundly unstable if the electrons were allowed to move up and down from the plane of the ring. In fact, this criticism so undermined the model that Nagaoka would withdraw it in 1908 in acknowledgement that the model just didn't work. Now, Thomson's model also had a good sense of analogy with a well-understood physical system. It, too, attempted to explain a well-documented but poorly understood phenomenon, namely the periodicity of chemical elements. Unfortunately, the five-ring system didn't match up very well with the way periodicity seemed to be shaping up with its 2, 8, 8, 18, etc. structure that had been found in Lothar Meyer's and Dmitry Mendeleev's tables. Additionally, Nagaoka questioned whether the positive charge could actually be penetrated by the negative charge, as this sort of idea had been rejected in the study of electrical current flow 100 years earlier. Nevertheless, Thomson's position at Cambridge kept his model at the forefront of the conversation, and when Ernest Rutherford returned to England in 1907 to take the professorship in Manchester, he picked up a couple of students with strong ties to what was happening at the Cavendish lab. This collaboration, along with the ones that will follow, will remake the model of the atom in ways that no one could foresee. Trying to describe Rutherford's work is a challenge. Describing the results isn't so hard, but one of my goals in this podcast is to give you an idea of how the results were arrived at, and that can be pretty hard to do because I've got to get you to see both the right kinds of pictures in your imagination and also understand why the research went in the direction it did. If I can successfully do this, I think you'll agree that Rutherford was easily the most gifted experimental researcher of his generation, matching in many ways the theoretical brilliance of Albert Einstein, his contemporary. While still at McGill, Rutherford, in his research on the alpha particles produced by radioactive decay, had noticed that they could be deflected somewhat in passing through matter. What he had done was to direct a beam of them through an increasing series of sheets of aluminum foil. He wrote of the results from this experiment, quote, "From the measurements of the width of the band due to the scattered alpha rays, it was easy to show that some have been deflected from their course by an angle of about 2 degrees. It is possible that some have been deflected through a considerably greater angle, but, if so, their photographic action was too weak to detect on a photographic plate. Such a result brings out clearly the fact that the atoms of matter must be the seat of very intense electrical forces." Unquote. What Rutherford had found was that these massive, fast-moving particles had had their normally straight paths of motion bent just a bit as they passed through the sheets of foil. What he didn't know was whether that was all that had happened to them, or if some of the paths were bent even more. The reason for this is that his detection equipment just wasn't sensitive enough to record a small number of alpha particles. When Rutherford moved to Manchester, he picked up a student from Cambridge, Hans Geiger. Geiger had developed a technique of recording the flashes of light that were produced when an alpha particle hit a phosphorescent screen as a way to detect radiation much more accurately than the photographic plates that Rutherford had been using. Rutherford had Geiger repeat the experiment he had done in McGill, and the result was confirmed, showing that alpha particles could definitely be scattered. This corresponded with a set of experiments that had been done with beta particles. If you recall, it had been shown that these beta particles were one of the three types of radiation given off in radioactive decay, and that they were actually electrons. This meant that they had much less mass than the alpha particle did, which should have, in theory, made them easier to deflect. It had been observed that when beta particles hit a metal plate, they produced a radiation from the plate. However, when an experiment to measure the scattering of beta particles was done, it was found that not only were some of them deflected, but that some were reflected straight back at the particle source. In other words, what had been discovered is that the radiation coming from the plate was in fact beta particles bouncing straight back. So what Rutherford had Geiger do was to see if a similar kind of set of measurements could be done with alpha particles. Now, to understand how hard this was to do, we need to talk a bit more about the experimental apparatus, specifically this detection method. The fancy name for what Geiger was doing was called scintillation detection. When an alpha particle hit the phosphorescent screen, the material would give off a little flash of light. The procedure was to use a microscope to count the flashes given off at different angles. This had to be done in a completely darkened room where the observer would have to sit for about 30 minutes to allow his eyes to adjust before he could make any kind of measurements. Rutherford and Geiger both knew that if there were any flashes to be observed out beyond the 2-degree mark, it was likely going to be really tedious work. So Geiger suggested to Rutherford that they bring in an undergraduate student who seemed to have an aptitude for minute, detailed work. That student's name was Ernest Marsden. The key turning point occurred when Rutherford was in the counting room one day and suggested in a sort of offhanded way that Geiger and Marsden look to see if there were any particles scattered directly backwards. The two had observed flashes at bigger angles than 2 degrees, but the number of flashes at angles bigger than that had fallen off pretty rapidly. In fact, Geiger had done a calculation that showed that the largest amount of scattering should be at 1 degree. It's clear that Rutherford didn't really expect anything to be observed, but on a hunch, he decided to have the two men give it a try anyway. When the experiment was performed, Marsden detected flashes at angles greater than 90 degrees, and some where the alpha particle was reflected almost straight back, as it had happened with the beta particles. There is an oft-quoted remark that Rutherford made regarding this result that also captures the increasingly militaristic tenor of the times. He said, quote, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you," unquote. So why was this result so surprising? Well, it goes back to Thomson's model, which was what Geiger was using to calculate how much scattering should take place in the experiment. This model had all the positive charge being spread out in a sphere. If a big old fast-moving alpha particle encountered this diffuse positive charge, it wouldn't be much affected by it, especially with all the little negative charges embedded inside that positive charge. Moreover, such a distribution wouldn't be able to reflect the positively charged alpha particle straight back at all. Now, since the experiment had used a very, very thin sheet of gold foil as the deflection target, there would only be a few atoms worth of thickness to do the deflecting. so there was next to no chance of having the alpha particle come straight back towards the source. Hence, the firing of a 15-inch cannon shell at a piece of tissue paper analogy that Rutherford used. Now, while this was a startling and profoundly important discovery, there was still a lot of work to do. What had to be done was that accurate counts needed to be made to figure out just how many particles were being reflected back, among another number of other considerations. To do this, Geiger had to build a much more precise alpha particle source that would allow for a very precise rate of emission to be determined. During 1909, the two men would refine their tools and methodology under Rutherford's direction until they had something really, really good. When they then took their data, they determined that 1 in 8,000 alpha particles were deflected at an angle greater than 90 degrees. Now, while this seems like a pretty small number, it was millions of times greater than what Geiger had calculated should be the case if Thomson's model had been correct. What they had done was prove Thomson wrong, but there was now no new model to take its place. It would take 2 years before Rutherford would publish a result. So let's think a little bit about how one might come up with an answer to this puzzle. When I was an undergrad and we were studying this sort of thing in a modern physics lab, Dr. Stringer, our professor, had us do an experiment by analogy. He had this big round piece of thin plywood that was about 2 feet in diameter that sat on legs that were about 2 inches tall. We were told that there was a shape underneath this cover that we couldn't see, and we had to try to figure out how big it was and what the shape might actually be. To help us figure it out, he gave us some spring-powered marble shooters. The idea was to shoot the marbles under the cover and see which way they bounced out. Now, it took us quite a while to sort of work things out, but eventually we got that underneath the cover was a circular object about 5 inches in diameter. So how did we know that? Well, when we shot the marbles in, most of the time they weren't deflected. In fact, we only seemed to get a deflection when we aimed the marbles pretty close right at the center of the big cover. Now, if the object underneath the cover had been squared, what it would have meant was that we should have been able to find a shooting angle where the marble either bounced straight back or wasn't deflected at all. That would have meant we were firing straight into the side of the square. We never saw that. This also eliminated any other answer where the object would have had flat edges. Another thing we tested was whether it mattered what direction we shot the marbles in from. In other words, if we fired them from one side, did we get a different result than if we had fired them from another side? What we found is that the distribution of the scattered marbles didn't depend much on the side we fired the marbles in from, which meant that there wasn't a preferred direction or axis the object was elongated along. Finally, once we determined the object was a circle, we could get a good rough estimate of its size by moving our marble gun a little bit to the side until there was no longer any scattering. This little experiment we did was a great description of what Rutherford was doing with Geiger and Marsden's data. He was trying to use it to figure out the size and shape of what was causing the deflection. The fact that some of the alpha particles had bounced straight back meant that there had to be a concentrated positive charge somewhere in the atom that had had a lot of mass. By looking at the distribution of scattering angles, Rutherford was able to determine that the size of this positively charged mass was much, much smaller than the atom and that it was nearly spherical in shape. Finally, he determined that the amount of the charge in this mass had to be about 1/2 the atomic weight of the element that made up the scattering target, a result that was arrived at by using a lot of different materials for the foil. This last result, which talked about the relationship between the positive charge of the atom and its atomic weight, was independently arrived at by the British physicist Charles Barkla through an analysis of the scattering of X-rays from various elements at about the same time that Rutherford published his paper. Barkla had concluded that the X-ray scattering had to do with the number of electrons per atom. So by using the scattering to measure the number of electrons, and recognizing that the atom had to be neutral, he was able to determine the amount of positive charge. Rutherford, Geiger, and Marsden's work led Rutherford to put forward a nuclear model of the atom in a seminal paper published in 1911. This model had a nucleus of positive charge that was about 1/10,000th the size of the atom surrounded by an equal number of electrons that orbited the nucleus. Rutherford acknowledged that his model suffered from many of the same problems that Perrin and Nagaoka's did, but he couldn't see how else to explain his experimental results. In other words, while he had answered some questions, the model raised a number of other issues to be solved. There is one final piece to this story that is important to tell at this point, and that is the discovery of what we call atomic number. While Rutherford had shown that the atom had a nucleus, and that the charge of that nucleus would be roughly about half the atomic weight of the element, he didn't have an exact measurement of that charge, nor did he fully understand how it was related to the larger picture in chemistry. This was an outgrowth of what he was using his model to do, which was explain his scattering results primarily, and maybe account for the elemental spectra secondarily. Gaining a deeper understanding of this relationship would fall to two other men. The first was a Dutch amateur scientist by the name of Anton Vandenbrook. Vandenbrook was a student of Mendeleev's periodic table, and over the course of his study of that instrument, he attempted to make improvements upon it. His first paper was published in 1907, which worked from an idea that Rutherford had put forward about the nature of the alpha particle. Now, it's important to understand that this was prior to the point where Rutherford had been able to demonstrate that the alpha particle was, in fact, an ionized helium atom, and so in the paper, he had suggested that the alpha particle was actually half of a helium atom with a charge of +1. Vandenbroek called this particle the alphon, and proposed that it might be able to replace the hydrogen atom in Prout's long-discarded hypothesis. If you will recall from the episode on the periodic table, Prout had suggested all elements were actually combinations of a single basic particle. Vandenbroek suggested in his 1907 paper that the periodic table could be seen as the incremental advances of this alphon, with each element having one additional alphon than the element immediately to the left of that element in the table. While the idea of the alphon was ultimately shown to be incorrect, Vandenbroek modified his hypothesis in a paper published in 1911 that just suggested that each element was heavier by 2 fundamental units of weight without invoking the alphon. In that same year, building on the work of Rutherford and Barkla, he submitted a short note to the journal Nature, wherein he suggested that the nuclear charge number of the atom would be the quantity that defined the position of the atom's element on the periodic table. Vandenbroek would refine this idea one additional time in a pair of papers in 1913, which incorporated additional scattering experiments from Geiger and Marsden. His work was used by both Niels Bohr and Soddy in their work related to atomic structure. The difficulty was that Vandenbroek's work was somewhat speculative and relied on the experimental efforts and data of other researchers. As such, he was unable to acquire evidence that directly supported his idea. This work would fall to Henry Moseley. Moseley was one of the research students who had gathered around Rutherford in Manchester, who worked on a variety of different projects. In 1912, he and a postdoctoral student on loan from Cambridge, one Niels Bohr, got to discussing an odd case in the periodic table. There was a great deal of debate about the positions of nickel and cobalt in the table. The two metals were adjacent to each other in the table, but there was some question as to which should be first. It's a problem known as pair reversal, where an element with a heavier atomic weight is placed earlier in the table than an element with a lighter atomic weight, because the first element's other physical and chemical properties better match placement in that group rather than in the later one. Moseley decided to develop a test he thought might resolve the question through an investigation of Vandenbroek's atomic number hypothesis. The test he devised involved scattering X-rays off of a target sample in a method similar to that had been used by Charles Barkla. Barkla had discovered that there were two different ways to produce X-rays. One using a Crookes tube, as Röntgen had done, and the other using electrons scattered off a metal plate. This second type of X-ray, called K-alpha X-rays, is what Moseley would use in his experiment. He devised a rather clever apparatus in which 14 metal plates, each made of a different element, could be inserted into the apparatus, which would then rotate each plate in turn into the beam of electrons. These would then produce K-alpha X-rays of specific frequencies. This turned out to be an excellent example of classic experimental design. Moseley would change only one thing, the type of material, and see how the X-ray frequencies changed. In doing this experiment, Moseley's results showed that the frequency of the X-ray depended on the square of the element's position on the periodic table. This strongly supported Vandenbroek's hypothesis that there was a single number that determined an object's position on the periodic table, and Rutherford's assertion that the number was related to the charge on the nucleus of the atom. As Moseley wrote in a paper published in the journal Nature in 1913, quote, "We have here a proof that there is in the atom a fundamental quantity, which increases by regular steps as we pass from one element to the next. This quantity can only be the charge on the central positive nucleus, of the existence of which we already have definite proof." Unquote. In 1914, Moseley published a second paper that extended the results to 30 more elements. With this relationship now definitely established, Moseley was able to apply his methods to resolve a number of outstanding questions related to both the ordering of the elements on the periodic table and also in determining whether certain substances which were claimed to be new elements were in fact unique, or if they were just a rediscovery of something that already existed. An example of this later application, taken from Eric Sherry's work on the periodic table, was the case of Japanese chemist Masataka Ogawa. Ogawa had claimed to have isolated a new element he called nipponium, which would have been placed under manganese in Mendeleev's table. Moseley was able to test a sample of the material and show that it did not have the required atomic number and thus wasn't a new element. At the end of Moseley's analysis, it was shown that there were only 7 gaps in the table between the elements 42 and 92. I say at the end of Moseley's analysis because his career was tragically cut short in 1914. With the outbreak of World War I, Moseley joined the British Armed Forces and was killed in the Gallipoli campaign, becoming, at least within the scientific community, a symbol for the tragic waste of human life and potential that war would come to represent. However, before that war engulfed Europe and shattered the empires and the assumptions that caused the war, there was one more model put forward relating to the atom. This model, too, came from a physicist associated with the research efforts in Cambridge and Manchester, and his name was Niels Bohr. His explanation of the atomic structure of the atom would forevermore change the assumptions of classical physics and push our understanding of matter in completely new directions. We'll take up that story in an episode titled The Quantum Atom. Now, before I sign off, I want to say thanks again to everyone who's subscribed to the show. We're getting closer to the possibility of a question and answer show, so if you have any questions about this history of the atom stuff that we've been going over, and you'd like to have those things discussed, be sure to leave a comment on the show's website, www.typepad.thescientificodyssey, all one word, .com. Also, leave a comment about what you think of the show. And if you'd like to rate the show on whatever service you're using to download and listen to it, that'd really be a big help in helping getting the word out about what we're doing here. Finally, if you know any groups that you think might enjoy the show, please feel free to promote it there. Dr. Sherry did a really kind thing. He was kind enough to post a link to a number of the physics and chemistry education list servers that brought a lot of traffic to the show. If you're a part of something like that and want to let your listserv or your group or whatever know about the project, I'd sure appreciate it. So until next time, full sails on your journey.